Good morning and welcome to Friday of week 5 of your Physics 5 a day. We're talking about nuclear reactors first here today, using this very nice diagram by Emoscopes via Wiki Commons. We don't need quite all the labels, so what's highlighted in green, that's what you need for your A-level. And for us, this is often coolant, so I've changed that label there. This coolant is often water, and we sometimes find that the moderator is water for our exam questions as well, water or graphite there for the moderator. Okay, here's our typical fission reaction that we saw yesterday. And the uranium-235, the stable uranium isotope, that's what the fuel rods are made out of here. To get this whole thing started, when you first start up your nuclear reactor, you need some neutrons to get it going. So to get it started, you wouldn't put all the fuel rods in, you'd put a neutron source in one of them. And then that gets it started. So uranium-235 nuclei in these fuel rods, if they absorb a neutron from your neutron source, they're going to turn into uranium-236, which is unstable, and then it's going to decay into our 2 nuclei there and our 3 free neutrons, which fly off with lots of kinetic energy. Once that happens, now you've got neutrons that can go back in at this end. So then you take your neutron sources out and you put some more fuel rods in. Okay, your 3 neutrons there, as we discussed yesterday, they need to be moving quite slowly to be absorbed by the uranium-235 nuclei. So they get chucked out at the end of this reaction and they're moving really quickly, and we need to slow them down. So that's what the moderator does. The moderator is made of something dense which slows down the nuclei. It doesn't absorb them, we still want them, but we need to slow them down. And remember, when they are slow, we call them thermal neutrons. So that's the job of the moderator, to slow down these neutrons so they're moving slow enough to be able to go back in this end. Okay, but we also saw yesterday that if all 3 of those neutrons are allowed to go on to then make 3 fission reactions, and then that will make 9 neutrons, and then we'll have 9 fission reactions, and that's a chain reaction, and we don't want that. We actually want to absorb 2 of these neutrons, get them out the way, and just have 1 of them go back in. So 1 reaction causes 1 more reaction, and so on. And that's the job of the control rods. So control rods are typically made of boron, which is very good at absorbing neutrons. And you can see, it shows in this diagram, that they're not pushed all the way in there. So you can push these in further or you can pull them out. And obviously the more you push them in, the more of these neutrons they're going to absorb. And if you push them all the way in, it'll absorb all the neutrons and your reaction will stop completely. But if you get it wrong and you pull them out too far, then you won't absorb enough neutrons, and then your reaction will get bigger and bigger, and that's very dangerous. So that is the role of your boron control rods. Okay, so let's assume now that you've got it all nicely balanced. You've got your uranium-235 and it's absorbing neutrons turning into uranium-236. That's doing fission. Your neutrons are coming out, they're moving very quickly, the moderator slows them down, and the control rods absorbs 2 in every 3. And then the 1 nice slow thermal neutron that's left goes back in and causes another fission reaction. Right, what's the point of all of that? Well, the point is, of course, that loads of energy is released in this fission reaction, and that energy is being carried by these neutrons. And so when the neutrons come out, they're going to heat up the moderator, and that heat is passed to whatever's coming through here. Now, as I say, for us it's normally water. So these neutrons hitting things pass on the energy and it ends up in a thermal store, and so basically the water coming through here gets hot and then it goes round there, and we're in a heat exchanger, so this water just keeps flowing round and round and round. But when it gets here, it's hotter than this cold water coming in, and so it passes the energy over to this cold water going in, which is hot by the time it leaves. So hot, in fact, that it's steam. The steam then turns a turbine, which turns a generator, which generates electricity. So this end of it here is just like a normal coal power station. Okay, and the last thing to note here is just why have we got a heat exchanger? Why not just have this water coming out and going directly to turn the turbine? And the answer is that this water has been passing by radioactive stuff. So it's possible that this water has little bits of radioactive material in it, and so you don't want that getting out. So this system, you keep the radioactive, anything that may be contaminated stays there going round and round and round, and then this water comes in. This is definitely safe water, just picks up the heat energy and then goes out again. So it's a safety feature. I might just add in one more safety feature there, the fact that the whole reactor, the core of the reactor, is encased in something that doesn't let radiation through. That's obviously another important safety feature there. Okay, right, when you think you're ready, have a go at the first question today, which is worth 4 marks. Okay, so the moderator slows down the fast-moving neutrons for 1 mark. The neutrons lose a significant amount of their kinetic energy when they collide with the moderator nuclei for the 2nd mark. The control rods absorb some of the neutrons for the 3rd mark, and this reduces the rate of fission reactions for the 4th mark.